Okay, part 2 of our sampling distribution notes. So from our sampling exploration activity that you did with the applet, you should have noticed that the mean of the sampling distribution always equals the mean of the population. But as the sample size increases, your standard deviation should always decrease. So as n increases, your sigma of the standard deviation of sample mean should decrease. Because again, the more data we have, the more accurate we have in case we do have a data set that's further out, it's not affected as much. So again, a reminder of what an unbiased estimator is. It is used to estimate a parameter as unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. And as we've previously said, your sample mean equals your population mean always, but your standard deviation is going to get smaller based on the larger sample size. So if we have the population standard deviation, we can take sigma and divide it by square root of n, your sample size. And this rule works as long as we have an approximately normal curve, as long as no more than 10% of the population is included in the sample. And when the population distribution is normal, the sampling distribution of the sample mean is also normal for any sample size n. So that's why it's very important to prove normal by stated normal or by rule of 30, sample size being above 30. And the central limit theorem states when n is sufficiently large, the sampling distribution of the sample mean is well approximated by a normal curve, even when the population distribution is not itself normal. And we can provide the central limit theorem as long as your sample size n is greater than 30. So let's look at an example. We have Army reports that the distribution of head circumference among soldiers is approximately normal, with a mean of 22.8 and a standard deviation of 1.1. What is the probability that a randomly selected soldier's head will have a circumference that is greater than 23.5 inches? Well, if it's asking about what is the probability, and I have a mean and standard deviation, that means that I can find z-score. So let's take x minus the mean, divide it by the standard deviation of 1.1. We crunch the numbers, we should get a z-score of 0.636. So this question is asking us, well, what's the probability that x is greater than 23.5, which we translate into z-score. That means we're looking for the probability that z is greater than 0.636. And because it's a greater than, we need to subtract from 1. So if you open up your z table, look inside your z table to find what is the area left of 0.636. We should get inside the table 0.7377. And again, since it's greater than, we want to subtract it from 1. So 1 minus 0.7377 gives us a probability of 0.2623. Or we could say about 26.23% of the soldier's head will have a circumference that is greater than 23.5. Okay, so this is nothing new to us. Okay, we've translated z-scores, looked inside the z table, found probabilities. So what's different? Well, let's change this problem up to instead finding what is the probability that a random sample of 5 soldiers will have an average head circumference that is greater than 23.5. Well, now we've changed our sample size. So again, sample mean stays the same. We still have our same sample mean from the previous problem, 22.8. But notice we're no longer just taking 1 soldier, we're now taking a random sample of 5. So we need to take that sample standard deviation 1.1 and divide it by square root of n, which is square root of 5. If we crunch the numbers, we will get a new standard deviation of 0.49. Now we can just translate it into z-score. So if we take the z-score, x minus the mean divided by our new standard deviation, 0.49, Crunch the numbers, we get a z-score of 1.43. So again, this problem is asking us to find probability. So we're looking for the probability that x is greater than 23.5, which we translate into z-score, probability that z is greater than 1.43. And since it is greater than, we are looking for 1 minus. If you look inside your z-table, area left of 1.43 should get you a value of 0.9226. So subtract it from 1, since we're looking for a probability that's greater. We should get a probability of 0.0774, or we could say about 7.74%. So notice the difference between here, okay? So this is what's the probability that a random sample of 5. Random sample of 5, average head circumference greater than 23.5. And again, notice how small, 7.74. We go back to the previous problem. Notice when we were just taking a randomly selected soldier, notice we got a much higher percentage, 26.23. Okay, so always if you're taking more than one, you're going to get a smaller probability because, again, let's just say that one you choose is maybe a higher or a lower value than the others. It's not going to affect it as much, okay? Which is why when we calculate the new standard deviation, when we have a sample size other than 1, we divide it by the square root of it, because we should get less variability. So let's look at another example. Suppose a team of biologists have been studying the Pinedale Children's Fishing Pond. Let X represent the length of a single trout taken at random from the pond. This group of biologists has determined that the length has a normal distribution with a mean of 10.2 and a standard deviation of 1.4. What is the probability that a single trout taken at random from the pond is between 8 and 12 inches long? So again, this is a straightforward z-table question. So first, let's find the z-scores. So we find a z-score for a length of 12 inches. So 12 minus the average, 10.2, divided by standard deviation, 1.4. Again, also find the z-score for 8. So 8 minus 10.2, divided by 1.4. So we get an upper z-score of 1.29. We get the lower z-score of negative 1.57. So this question is asking about probability. So we're looking for the probability that X is between 8 and 12 inches. And we translate to z-score. That means we're looking for the probability that our z-score is between 1.29 and negative 1.57. So when we're looking for in between, take the probability that the z is less than the greater z-score minus probability that z is less than the smaller z-score. Look inside your z-table. Area left of 1.29 should get you 0.9015. Area left on the z-table of negative 1.57 should be 0.0582. If we subtract the two, we should find a probability of 0.8433, or we could say about 84.33%. So let's change it up. And what is the probability that the mean length of 5 trout taken at random is between 8 and 12? Okay, so notice the only difference now is instead of just taking 1 trout, we're now taking the mean average of 5. Well, if we're taking the average of 5, that means our standard deviations are going to get smaller. Okay, so we need to calculate a new z-score because we're now taking our standard deviation of 1.4 and dividing it by square root of 5 on both sides. So if we crunch the numbers, we're now looking for finding the probability that X is between 8 and 12 would be that finding the probability that Z is between 2.87 and negative 3.51. Again, always take probability of the larger z-score minus probability of the smaller. If you look inside your z-table, area to the left of 2.87 is going to be 0.9979. And the second one is a little tricky. If you look at your z-table, you notice you don't have a value smaller that exactly fits a negative 3.51. Just take whatever's smallest. Notice the smallest value on the z-table is 0.002. So just take whatever is the smallest negative z-score. And if we crunch the numbers, subtract, we get a probability of 0.9977, or we could say about 99.77%. So notice the difference between this answer and the previous. Okay, we had about 84% if we just chose one trout between 8 and 12. Notice when we average 5 of them, very, very high percentage, almost all, right? 99.77%. So again, make sure to read questions carefully. Make sure to see, is it asking for a single unit or is it an average of a certain value? And take that standard deviation and divide that standard deviation by the square root of n if needed. So now let's do a working backwards. What sample mean would be at the 95th percentile? And again, we're going to be assuming that our sample size is from 5, still taking 5. So again, this is a working backwards. So working backwards means we need to first look inside the table, the z-table, for 0.95. So what z-score corresponds to 0.95? That would be a z-score of 1.65. And now we can insert that z-score of 1.65 into our z-table equation. So 1.65 equals x minus 10.2 divided by our standard deviation 1.4 divided by our square root of n, which they already told us is 5. You can use your numerical solver on your calculator, solve for x. Or again, we could multiply both sides by 1.4 divided by square root of 5, both sides, and then add 10.2. Either way, we should get an average length of 11.23. Okay, so what sample mean would be at the 95th percentile? That would be 11.23. So let's look at another example. A soft drink bottler claims that on average cans contain 12 ounces of soda. Let X denote the actual volume of soda in a randomly selected can. Suppose that X is normally distributed with a sigma of 0.16 ounces. 16 cans are randomly selected and a mean of 12.1 ounce is calculated. What is the probability that the mean of 16 cans will exceed 12.1 ounces? So again, we're not dealing with a single can, we're dealing with 16 cans. So first is we need to find the corresponding z-score for that. So z-score is taking x minus the mean, so 12.1 minus 12, divided by our standard deviation, which is 0.16, divided by, again, we're taking it of sample size n equals 16. So divided by square root of 16. Crunch the numbers, we should get a z-score of 2.5. So this problem is asking us to find the probability that x is greater than 12.1. That means that we are looking for the probability that z is greater than 2.5. And since it is greater than, we subtract from 1. Look inside the z-table. Area to the left of 2.5 should be 0.9938. But again, we're subtracting from 1 since it is greater than. And our final probability should be 0.0062. So very, very small. What's the probability that the average of 16 cans will exceed 12.1 when we want it to be 12? Is approximately 0.62%, which is good. If you think about this as a real world example, okay, bottling companies have machines set at a certain mean, right? You know, it's better to underfill than to overfill, right? Because if you overfill, you'll have a big mess. So again, you do want a very, very small percentage to be overfilled on this bottling example. Otherwise, you're going to be wasting a lot of product and have a lot more mess to clean up. And that concludes sampling distributions part 2.